This is OpenStax Chapter 6, number 84. Here we're trying to calculate the maximum speed of a raindrop, whether there's air resistance or not. So first we're going to calculate in the absence of air resistance. And so if you look at what they're asking you for a velocity after it has fallen this far. That's like a final velocity. It's dropped, so we can imagine we have an initial velocity of 0. We can think this is like a delta y. And because if we're ignoring drag, the object would be in free fall, we can say we also know what the acceleration is. So I'm going to first use kinematics to solve for this final velocity. I'm going to say that my acceleration is negative 9.8 meters per second squared because we're ignoring air drag. V initial is 0. Delta y is negative because it ends up lower than it started. They give me 5 kilometers. I'm going to do it in meters because my acceleration is in meters per second squared. And I want to find out my final velocity. So this is the equation that involves those 4 variables. Here I've plugged in all the variables, and here I've solved for my final velocity. Remember, you're going to be taking the square root of a number. Whenever you take the square root, there's 2 answers, a positive and a negative, and you have to choose which one it is. Well, in this case, it's a negative velocity because it's moving downwards. For part B, we're going to use the formula for terminal velocity. So if there is air drag, we can imagine that this object, which is not really doesn't really have that big of a mass, will definitely reach its terminal velocity or terminal speed before it travels those 5,000 kilometers. So I'm just going to look at what is the terminal speed of something that has these values. So my formula for the terminal speed is this is square root of 2 times m times g over rho times c times a. So the first thing that makes this problem a little tricky, this rho, that's the density of the medium or the fluid that the object is moving through. My object is a raindrop. The fluid that it's moving through is air. So this has to be the density of air, not the density of the raindrop. So we're going to plug in, eventually we're going to plug in the density of air, which is 1.21 kilograms per meter cubed. That's a value I would give you for the quiz. So what is this density? Well, that's the density of the raindrop, and I can use that to figure out the mass of the raindrop. So let's do that. So that's the density of water. Our formula that we haven't quite learned, but you probably already know it. Density is equal to the mass of something divided by the volume of something. Here I've just rearranged it because we're trying to solve for the mass. And then here what I've said is the volume of this object. Well, this object is a sphere, so here's the volume of a sphere. And now I can plug in the density of the raindrop. And r is the radius of the sphere. They told me that the size across is 4 millimeters. That means the diameter is 4 millimeters and the radius is 2 millimeters. I'm going to do my units here in meters. So it'll be 0.002 meters, and that gets cubed. And then I can find the mass. This is the mass of the raindrop, 3.35 times 10 to the minus 5 kilograms. So that's what we're going to plug in here. Next, we need to look up the value for C. From the table in the textbook, we can say that the drag coefficient for a sphere is 0.45. And then finally, our cross-sectional area. If it's a sphere, the cross-sectional area would be like a circle that has an area of pi r squared. R, again, is the radius, 2 millimeters, but here I've put it in meters. So we get that the area is 1.26 times 10 to the minus 5 meters squared. And now we can plug in all of these things into our terminal speed formula. And when you do that, you get 9.78 meters per second. So much, 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 much slower than what we found here. Luckily, right, it would be pretty horrible if raindrops fell going that speed.